Okay, I think we'll kind of get started. So I'm Mark Bollefeys, professor here in the department, but I'm also in the Department of Computer Science, but I'm also working at Microsoft, leading the Spatial AI Lab. Oier Mees is one of the researchers in the lab there. He's in particular really driving things forward on robot learning and so on. And we identified that this was something that was missing at ETH in the curriculum, a course really focused on robot learning. And so we decided that then Oier could essentially fill in that gap. And so that's what you'll have here. So I'll serve as the mentor also for the course. A lot of people from the lab will actually also help as TAs and so on. So you'll also see there will be some robots to play with actually during the course, all these kind of things. So we've taken care of all those things on the ETH side. Although Oier at Microsoft will essentially teach the course, it's fully integrated within ETH and we'll have all of the usual things and resources and so on. Okay, and so without further ado, I'll let Oier kind of take over. Maybe one more small thing.
Yeah.
So Oier was, did his PhD not too far from here where is it again?
Freiburg.
Oh, you have it there? Okay, perfect. Yeah, in Freiburg. There. And then essentially after that did his postdoc at Berkeley, worked there with Sergey Levin and people like that. And then now he's here in Zurich. And so, yeah, I'll leave it at that.
Thank you. Thanks everybody for coming to this first lecture. Do you hear me okay also in the back? Yes? Awesome. Really appreciate you all coming. I'm very excited for this course. Also appreciate you all coming despite the weather today. As Mark pointed out, I spent the last 2 years in sunny California, and the winters there were definitely different to the winters in Zurich. But still super excited to be here. And talk a little bit about robot learning. So maybe I will today start first with some of the course logistics. So if in case you need to reach me, my contact details are here. But more importantly, first I want to talk a little bit about to show you the why behind this course. So the collage here represents essentially work I have been doing during my time in Freiburg, in Berkeley, and also now in Zurich. And so these are not really just cool demos, but they are experimental results of the very robot learning frameworks that we will be studying in this course in this semester. So from the drawer opening task here with the Google robot on the right to mobile navigation, well, I think the pointer doesn't do, or drone flying. We will use the same imitation learning and reinforcement learning algorithms. These are using the same algorithms that you will be implementing in this semester, first with the individual homework assignments and later with real-world group projects. Of course, managing a course at this scale is a massive team effort. And I'm incredibly fortunate to be joining this semester by a team of exceptional TAs. Our team includes Alexei, Jonas, Liam, Nicola, Tiangshu, Shimon, Nicole, and Sador, as well as Carl, who's on the next slide. They are working really hard to help create and validate the homework assignments. And they will also be your main point of contact to answer questions and help with the exercises on the Thursday sessions. Maybe the TAs that are here, you can stand up so people can see who you are. And by the way, like we still have open TA positions because like the course seems to be very popular. We have 290 enrolled students right now. So if you're interested in helping also TA this course, especially if you're like still a master's student, please also contact Liam, Jonas, Alexei, and so forth. We will be excited to talk to you about if you can help us with the TAs. So without further ado, the plan for today is to cover like the course logistics first, and the goals and logistics, and then covering a little bit on like why you should like study robot learning. This course is not really about spending all the semester just like training VLAs, etc., but it is trying to be a comprehensive curriculum where we will first kind of cover the basic algorithmic frameworks, as I said before, from imitation to reinforcement learning, and also expose you to different tools and philosophies also in robot learning. And so we will cover fundamentals first in the first kind of half, in the first part of the course. And then we will also have some hands-on experience with the real robots. And we will also cover frontier models and more advanced topics in robot learning towards the end of the course. But the really most important goal of this course is to inspire you. Robot learning is really a fascinating field because like you get exposed to everything from high-level frontier modeling down to like low-level PED control that actually moves the robot hardware. And in computer vision and NLP, as you all have seen, we have witnessed this like massive paradigm shift, right, where we've went from like individual kind of like tailored specialist models that were doing like all these things like translation, object detection, image captioning, and so forth, to kind of this more transformer-based foundation models. Like this lead to essentially like the ChatGPT moment, right, in computer vision and like in AI in general, right? And in robotics, we are kind of standing on the shoulder of giants, right? So we have decades of incredible progress in model-driven control, and more recently, we have begun adopting the like transformative power of many of the advances made in the other communities, like in vision and NLP. And as you can see, like by this arrow, like and specifically the word "you" in the slide, we are now kind of on the verge of the ChatGPT moment for robotics. And my hope is that by the end of the semester, some of you will find this field interesting enough to essentially like join and help us build it. All right. So before we start talking about robot learning, I will briefly cover the course structure. So we will here is the website with all the information. On Mondays, we will have first around 45 minutes of lecture, usually given by me, where we will, as I said before, cover like a lot of the algorithmic framework and fundamentals, followed by a paper discussion from like student-led paper discussions. I will talk about this in the next slide in a second. And then throughout the course, at the end of this, we will have guest kind of lectures or spotlights. Maybe not every week, but on most of the weeks, we will have like around 20 minutes or something from like different researchers from both industry and academia, kind of presenting some of their advances and cool work. And I'm trying to kind of fit them like topic-wise that these researchers more or less like are experts in the field or topic that we will be covering like that particular day. On Thursday, we will have the TA-led practice session. Here, we will cover essentially the homework assignments, discuss or give feedback, answer any questions you might have about the homeworks, On some weeks, like the TAs will also cover the solutions for the previous assignments and so forth. And in general, there will be 4 assignments first, individual assignments, before we move to the group projects with the real robots. So for the paper discussions we will be doing on Mondays, in the project website for each session, you will find around 3 different papers. And how we will try to do this, we will see if it works with the number of students we have. But the idea is that we will more or less have groups of 4 students, and we will essentially have like one group that kind of will present the paper, and another group that will, be kind of reviewer too, or will try to like point out maybe some like some things that they could have done better, or critique a little bit the paper. And so this will be around approximately 15 minutes per paper, ideally. So I have put the link on the website, but if you want, you can also just scan the QR code here right now. This will take you to the form where you can sign up for one of the papers that you like, that you would like to present that day during the semester. And you can also decide if you want to more be on the group that presents the paper, or, yes, we have a question. This is separate from the project group, yes. Yes, so this will be like, essentially like after the lecture, like today, like I will be well, today there is no reading club, but like starting next week, after the first 45 minutes of lecture, this will be student-led paper discussion. Yes? Yeah? Sorry, I didn't get the question. How many papers? Just one, yeah. Yeah. So I think also because of the high number of students, I don't know how many will keep enrolled, but I think like it should be one. I mean, obviously, like I would recommend everybody to like read all the papers that are recommended for all lectures. But in terms of like kind of presenting with your team, it will be just one, because there are also like other like assignments, so it doesn't make sense to ask too much. Speaking of individual homework, as I said before, we have divided the course into 2 parts. In the first half, you will be working on individual homework assignments. And here are more or less the topics and the dates you will have to submit these assignments. We will use an autograder to check your assignments. And yes, I think the first assignment should be out by the end of this lecture. Is this correct? Yes, the TA says yes. Cool. And here is the GitHub link where it will be published. But this you can also find on the project course. Maybe one small advice for the homework assignment. A lot of the homeworks, maybe not the first one, but they are based on training like neural networks, robot control policies, and although we try to make the homeworks faster to train by making the environments more simple, the domains simple, that like it doesn't require a data center to run this model, in general they still take some time to train. So my advice is that please don't start the night before the deadline trying to solve like your exercise, because your model might not have enough time to train or converge, or maybe you made a mistake, you need to like retrain your model. So like please like start before like the deadline night. For the course grading, I'm sure everybody will do amazing for everything. We have decided more or less to divide this in around 20% for the paper presentation and discussion, 40% for the practical homework, and 40% for the group project that you will do in the second half of the course with the real hardware. So there is no final exam, but there is some work to do, so you kind of get familiarized with all the frameworks and tools and research in robot learning. Yes, so feedback is really welcome. It's my first time teaching a course at this scale. Also for our TAs, it's the first time. And we are really trying hard to offer a great course. But for sure, we will make some mistakes because we are making things as we are going. And we will try to send every few weeks surveys to like a subset of the students to kind of get feedback on, what are we doing well, what can we improve, and so on. So yeah, just wanted to let you know that also because of the large number of students, it makes things a bit more difficult maybe to scale, but we are trying our best and hope that we will offer a great course. All right, and with this, I think we have covered the logistics. Oh, there's one more question. Sorry, I need a microphone, I don't hear.
Yeah, just because it's always a problem with project-based courses, how is the compute situation, let's say?
Yeah, so for the first, for the first homework assignments, you should not need a lot of compute. It should be possible to run these on like a desk, like a PC. I think for the second half of the course, where we will do like the real robot group projects, we are trying to get access to more compute so that we could also do a little bit more, use bigger models and do a bit more cool stuff. But we are working on it.
Sorry, you said that in the Excel sheet it says present in group and create size in group. Should we sign up for groups on a platform, or how do you manage that?
For the paper discussion?
Yeah.
The question is if you should sign up for one group?
No, the question is that should we just write our names, or should we make a group on a Google Docs, or I don't know how you work with that.
I think you can just write your name. I think it's fine.
Thank you.
Let's not overcomplicate it. This is different from the groups that you will be doing later for the real robot project. It's just to present a paper.
Could you maybe talk a bit more about the final project, what it's going to be, or what roughly the goal is there?
Yeah. So I think I have a slide later, but essentially we have purchased a fleet of 50 SO101 robots, thanks to the generosity of Mark. So these are really cool robots. It's from Lee Robot, which also have a puppeteering setup. So it's really easy also, to collect some demonstrations if you want to try to learn a new task with the robot. We will. The idea is that we will offer a set of canonical projects. Sorry. Just because the load for the TAs would be way too big if we did 50 different group projects with these robots. But we will try to find a way so that there is like this set of canonical projects that you kind of should be like more or less straightforward to implement, and you get some hands-on experience. But ideally, we will also try to give some time in case you want to do some more advanced things with it, and you're like creative and want to do some maybe more complex things. We will try to fit this in also. But yeah, we'll get to that like in around 6 weeks or so. Yeah.
Okay, thank you.
All right. Okay, that's a lot of questions, but yeah.
So I just want to ask for clarification on the paper discussions again.
Yes.
So each group, so there is like the criticizing part and there is the presentation part. So does each group has to just choose one of these, or does each group has to present at some point and then criticize also at some point? So
I think the original idea is that you either present or criticize. I think we will see how many students are, because we have to fit somehow all the students in this time slot. So we will start with that, and if we see that this is not working out, like we can maybe adapt it or something. But that would be the idea, that you at least either work on the on one of the teams at least. Yeah. All right. Mark also has a question.
No, it was to clarify. I think for the projects, we'll talk about it later also, but I think the idea was, on the one hand, there will be these canonical projects, that should allow you to get kind of good grades and everything, but then there will also be more challenging projects. Also for some of you, I know some of you are PhD students also in the class here and so on. So depending on where you're at and what you're interested in, you might also be able to do really projects that go further. Also, if you're a PhD student, that align maybe with your research, and then we can select an element of that would fit as a project. So we'll have that flexibility to do one of those canonical projects with your team, or actually also to kind of go for something that's more challenging, that's maybe you need already more background to do it, or you need resources that we might not be able to provide. But if you already, as a PhD student, have a robotic platform available, then maybe it makes sense to try something on that. So that's a little bit the way we're thinking about it at this point.
Mm-hmm. Thanks. All right. So now that we have cleared the logistics, I want to move on a little bit into robotics and robot learning. So I'm going to start out with a little bit of history because, as you all know, robots really have long captured like our minds, like for kind of serving like as a blueprint for what we are like building today in terms of robots, right? And this timeline is just not like like a cinematic timeline, but it's also a sort of like a history of like the expectations, our evolving expectations for like autonomy. And so in the early 20th century, like we started with like characters like the Q automaton, or like in Metropolis. So these are like really old. It's like over around like 100 years old, right? And by the 60s, Rosie the robot is kind of like a very popular character, which shifted, like the first robots were kind of showing more like the industrial automation kind of like a blueprint, right? And then our expectations shifted more towards utility and service, and then with Star Wars, with R2-D2 and so on, like we started to think of robots more as social agents with distinct personalities instead of just like tools, and kind of like more collaborative personalities that then also led to things like WALL-E, right? But moving to reality, like why do we actually build robots? So while science fiction kind of explores our imagination, the why is kind of grounded in the necessity and the tremendous potential that robots have for good in our society. Because we are moving towards a future where autonomous systems perform tasks that are fundamentally either dangerous or kind of distant and demanding. So this can be from the frontiers of interplanetary exploration to helping explore the depths of our oceans, where these are really hostile environments for humans to survive in. And also robots allow us to automate some let's say dirty and dangerous jobs, let's say underground mining, for example, or they can help after natural disasters and sort of search and rescue operations to keep people out of harm's way. As well as they also have a lot of applications in our healthcare system and in medicine, right? But perhaps more critically, we are also looking at robots to solve kind of a looming social crisis, because as our Western societies grow older, we will need more people to help us, and having robots that can assist and sort of perform personalized assistance and care at home will hopefully make our lives also a little bit easier and reduce the burden on our healthcare systems. I want to start now with a video that maybe some of you already have seen. Is it playing? This is Shaky the robot. So to understand where we are now in robotics, I think it's good to kind of see where it all started.
At SRI, we are experimenting with a mobile robot. We call him Shaky. Our goal is to give Shaky some of the abilities associated with intelligence, abilities like planning and learning. Even though the tasks we give Shaky seem quite simple, the programs needed to plan and coordinate his activities are complex. The main purpose of our research is to learn how to design these programs so that robots can be employed in a variety of tasks, ranging from space exploration to industrial automation. Shaky operates in this experimental environment of rooms, doorways, and simple objects. The top lens belongs to Shaky's television camera. He uses it to obtain visual information about his own location or about other objects. These walls were made high enough so that Shaky cannot see over them with his television camera. Shaky uses these feelers, or cat whiskers, to tell him if he has bumped into anything. He can push objects with this push bar. The programs controlling Shaky reside in a large
it couldn't really
PDP-10
grasp
computer
object, but it could
and
push
occupy over
objects around.
300,000 36-bit words of storage.
So this was kind of
Shaky
the state of the art
with the computer over a radio link.
This was kind of the state of the art in 1966. This was a robot developed in Stanford, and it essentially was planning everything. It kind of didn't follow a script, but it was doing planning. Are any of you familiar with the A-star path planning algorithm? Well, amazing. So that algorithm was actually developed for this robot, fun fact. So this is kind of where it all started. Shaky was doing maybe many of you know, this sense, plan, act kind of loop. As you've just seen, it had this TV camera to kind of do the visual scene analysis, and then it had sonar range finders to detect the distances to all. It was essentially using A-star for minutes or half an hour before it decided what is the next move I can do, and then push the objects and so on. Sorry. And from there, I think in the kind of 70s, 80s, and 90s, as you probably all know, we kind of moved towards more this industrial automation, where we use industrial robotic arms for manufacturing, like let's say a car assembly and so forth. And these actually don't work too different from like Shaky the robot in the 60s. It's very, very similar. They sense the world, plan a geometric plan in like their known map, and then act with like really high precision. And this has been incredibly successful, but only in structured environments, because essentially like they are state machines. So they're only as good as the logic that we can program into them. And these robots are more or less like, maybe now less, but they used to be like very, very blind. So if, a part on the assembly line, like kind of like change, like they would not really like adapt to those changes. And so the goal in our course is to move beyond these like closed world assumption. We want to explore how robots can move past rigid state transitions and instead kind of like use data-driven algorithms to handle like the edge cases of the real world. Maybe as a kind of like a more visual example, you might know some of these videos from YouTube. For example, these are like some humanoid robots, some of them also from Boston Dynamics, which are like represent some of the most impressive hardware that we have built. But even with like really world-class engineering, they typically have been relying on near perfect state estimation, right? And so this is like also these are videos from the DARPA Robotics Challenge in 2015, where kind of like the humanoid robotics kind of started to gain more momentum. And I mean, it's really interesting to see like how even simple tasks as like, opening a door or like opening a valve, like makes the robot like flip backwards. It's like, it's really funny. And then a few years later, like this is Boston Dynamics, the Atlas robot. You can see, you already see like they have QR codes all over the place because, that's what they use to kind of like have this like perfect like world model or like state estimation to understand where is everything at all times. And if you are even like, a few centimeters off, like, like catastrophic things can happen. And, even like more recently, ouch. Similar issues also happen when they do like things like parkour, right? So these are like really more or less almost blind movements, or they assume perfect knowledge of like all the environment and even the slightest like error in perception or planning results in these robots like falling and breaking like their expensive hardware. This brings us to Moravec's paradox, who was a faculty at CMU, who formulated this paradox back in 1988, and this kind of like captures why it is like so challenging, why robotics is so challenging compared to other branches in AI. So he observed that essentially abstract thinking, so the high-level reasoning we humans typically find difficult to do, right? Like complex mathematics or like strategic planning or playing chess or something, is actually relatively easy for an AI to compute. And we have had algorithms that beat like human chess players and so forth for decades now. But the real paradox is sensory motor skills, right? So basic physical interaction that animals and even toddlers find effortless is incredibly hard for AI. Because essentially there is like no training data. They cannot like crawl the internet to understand like how to, like grasp a bottle and drink from it. And you can see this like a little bit on this images over here. Here is an example from my PhD, 2019. I was trying to grasp this mug desperately with my PR2 robot in Freiburg. And, this was based on point cloud observations, analytical grasp, pose, estimation, and whatnot. And you see, like, it doesn't really work. And here, boom, it breaks the mug in two because it grasps too hard. So, yeah, we've made some progress since then, but it's really like fascinating, right? And then you see like this orangutans, like they can even use like tools just like by looking at others and imitating, and it looks so effortless, right? But even this basic, just like grasping a simple mug with a robot hand is like so difficult. Yeah, so this brings us to the core of this course. So really, if we want to move past this, like, rigid state of machines on the factory floor, we need like a different approach. And robot learning is the study of algorithms that enable a robot to acquire new skills or adapt to an unstructured environment by learning from data and experience rather than relying on, let's say, like explicit or hand-coded programming. And this diagram, like, I try to illustrate this a little bit on the challenge we face. So on the one side, we have kind of the robotics, which is like rooted in the physical world, and traditional, we engineer solutions to it, we build models for it, and so on. And on the other hand, we have machine learning, which has really like thrived in the digital world with data-driven solutions that can generalize with massive amounts of data. And robot learning is essentially the synthesis of these two. So it's about bringing generalization into the physical world to solve problems that are too complex to engineer manually. And how do we actually bridge this gap of Moravec's paradox? So the answer really lies in robot learning. So in this course, we will define robot learning simply as solving robotics via machine learning. And so on the left here, I have put the pillars of robotics. So let's say perception and control. These are, let's say, the what of like how the robot sees the world and how the robot physically moves within it. And as I said before, like historically, we've like done a lot of like great like model-based work on this. And on the right, we have the how, the machine learning. This is like the toolbox we will try to use to fill some gaps with this data-driven approaches. And we will look into limitation learning, reinforcement learning, representation learning, and all these things from machine learning. Now, before we get deeper into the algorithms, maybe let's talk about how we define robots. So on the left, we have dishwasher. In the middle, we have the Da Vinci, the surgical medical robot. And on the right, we have ChatGPT on a phone. Maybe you could like talk for 30 seconds to your neighbor and discuss if you think that any of these are a robot, and if so, why? Somebody wants to share what they have discussed very quickly? Alexei, just put the mic to someone you find. Oh, Elisabetta.
Yeah, we were discussing a bit, and yeah, we think the dishwasher, definitely it is a robot because it kind of changed the physical state of the world by operating something. ChatGPT, definitely it is not a robot in a traditional sense because you can have some intellectual interaction with it, but then the word stays as it is. And while the machine that doctor uses, it kind of depends on whether it is only analytical or whether you can actually perform something by using it, and if it is actually changing the world. But if you're controlling the machine yourself, then yeah, it is not really a robot because it's not automating the task.
Yeah. Yeah, thanks. Yeah, that's really a great summary. So you correctly identified. right? So for like the surgical robot, like this is essentially like a teleoperation. I mean, it does like some correction for like shaking of the humans and so on, but it's not like autonomous in a sense. It's not like, doing the surgery like instead of the doctor, right? And for like the ChatGPT on the phone, like it doesn't have like an embodiment, although it has like very like high level like reasoning capabilities, right? So yeah, in robot learning, we are really interested in the intersection. We really want the reliability of an appliance, the physical dexterity of a surgical arm, and the general purpose reasoning of a foundation model. Good. We'll continue. Where's my pointer not doing? So this brings us to the fundamental question of why don't we already have autonomous robots in our homes, for example? This is a video from 2007 from Stanford, and it shows a robot called the PR1 performing a bunch of useful everyday tasks, such as tidying up a room. And maybe for those of you who are not familiar with robotics, these tasks really seem easy and trivial. But as I said before, like they are actually quite challenging for AI models as it requires like common sense understanding about how to operate in unstructured environments. In reality, this robot was not autonomous, but it was being teleoperated, which, if you think about it, is actually a great sign because it means that we have had the hardware to perform, like similar like tasks, like tidying up a room since 2007. But what has been missing is essentially the software or the brain of this to make it autonomous, right? While the PR1 in 2007 showed us what is possible, still the hardware landscape has fundamentally shifted on two critical fronts since then. On the left, you see like the explosion of humanoid robots. We have moved from, let's say, like isolated like research prototypes to really a competitive industry of sophisticated, even commercially available platforms from companies like Figure, Tesla, Boston Dynamics, and so on. And these are like embodiments that are capable of doing now way more dexterous tasks than the PR1 I was just showing from 2007. But as we discussed before, like a robotic platform without a brain is like essentially just a puppet. So this is why the image on the right is perhaps maybe even more important, or at least as important as the hardware, because this represents also like the progress we have made in AI in general by the availability of massive compute through like improved GPUs and so on, right? So back then in 2007, like we simply didn't have the processing power to train models that could, that would scale to the required like generalist intelligence. While today we really have like these clusters that run this like massive like scaling laws that work for NLP and vision, for example. We've looked at hardware and compute. But now we also need to talk about, like the data that kind of like fuels all of this, right? To understand why we had a ChatGPT moment in language, but we are still waiting for it in robotics, you have to look at the sheer scale of information being consumed. To make these numbers a bit more easier to interpret, I tried calculating the average time it would take a single human, to read or process this entire data sets. So ImageNet, it would take around 2 years, like constantly just reading like the training set, right? And ImageNet is like now like it's quite some time ago. GPT-2, which is a model that still, by AI standards, like doesn't show maybe some of this emergent like capabilities from like later models, but still is like a decently sized model, it would take around 60 years to read its entire training corpus. And well, like these circles are not really to scale, I'm sorry about that. But Llama 3, it would be like 90,000 years, right? Yeah, so this really also like is equally, shows you like how progress in like AI has driven this recent advances. In terms of, finally, we come to the models themselves. I won't go into too much detail here, but we've really see like a, as you all know, like a breathtaking progression in algorithmic intelligence over the last few years. You know, we started with computer vision, moving from simple classification to models that really like parse the world with near pixel perfect accuracy. Then came AlphaGo, which proved that reinforcement learning could master long-term strategic reasoning, outperforming world champions. And now we even have multimodal models like Gemini. So this is really like impressive, right? And I think in even like maybe like one thing to note in AlphaGo is that it's not like, I think for the AlphaGo, it's not just about like that this model was able to beat like the world champion, but I think for like scientists, like the most interesting part of that was like this move 37. Maybe some of you have heard it. This was like a move that like the model did like during I think the second match. That was like so alien that first people thought that you know, it hallucinated or made a mistake, but then realized that it was kind of like a new strategy that, you know, it came up with by itself that no other human had thought of doing before. And so essentially, I think for robotics, we also want to move a little bit from, you know, this hand-coded era to the discovery era, where robots solve physical problems in ways we also haven't maybe imagined ourselves yet. And this brings us to the North Star for the field of robot learning, which is achieving generalist robot policies. As I was saying before, we are moving away from this era of specialist models that only know how to do like one task or one thing on one specific piece of hardware. And here the vision is really to build like robot foundation models that can take, you know, like a large robotic data set as an input and output actions for any task on any robot in any environment. And so in this course, we will cover also like first the algorithmic frameworks used in robot learning before we dive into some of the more advanced topics that revolve around answering some of these questions, like where do we get this data from, how can we model such large heterogeneous distributions, and so forth. And I think, you know, if you kind of think about in the future, we are not there yet, but I think you could imagine a future where you can just like download your kind of like favorite robot brain online, and then out of the box, your robot starts showing like reasonable behavior in a useful manner, you know, for any robot, like in a kind of plug and play sort of fashion. To close out this introduction, I want to show that we aren't just talking about like a theoretical future, but this is one that is being actively built right now. So on the left here, you can see the OpenX embodiment data set. This was a massive international collaboration with over 200 institutions around the world in 2004. That was trying to create, like, let's say, like the ImageNet data set for robotics. And we pooled together data from like 22, I think, different robot embodiments. Everything from, you know, single arms to dual arms to navigation robots and so forth, to essentially create like this huge data set in like a common like format that allowed essentially the community to start like developing and iterating on kind of this more like generalist robot policies for the first time. And on the right side, you can see some of these examples, example models that are first models that have been being trained on this data, plus some additional like Octo, Groot, RT2 from Google, Pi0, and so forth. So to finish this introduction, I want to give you a sneak preview of how this works. So let's start with a basic example. So when you typically train a robot policy, the model takes as an input a current image observation and a task instruction. Typically, it's a natural language instruction nowadays, such as like pick up the spoon. And then the model predicts a sequence of actions like end effector poses that allows the robot to achieve this goal. And now imagine that instead of doing this for a single task, we want to train this on a larger, diverse, heterogeneous data set. So if we squint a bit and we replace the robot image with the more regular internet image, like here, like the Statue of Liberty, and we replace the instruction with something like caption the scene, please, and then the model like answers like, oh, this is this picture depicts the Statue of Liberty. This starts to look really familiar for everybody who has paid attention in computer vision, right? Because this starts looking like a vision language model. So the key idea that much of the latest advances in robot learning build upon is that we can view robotics as a similar problem where we are trying to learn a powerful model that maps from images and instructions to answers, just that in our case, the answers are not text, but they are robot actions. So this means that the way we, by formulating the robotics problem as a multi-model sequence modeling problem, where we have language tokens, image tokens, and action tokens, we can also, as an advantage, we can leverage many of the advancements made in other communities like in vision and NLP to drive progress in robot learning. Okay, so now probably like all of you are thinking this. So are you saying we can just train a large transformer on robot data and like we are done? Is this all this is about? Not quite, luckily. Because there are actually like some key ingredients and differences that makes robotics like harder to just like transfer all of these like things from the other communities, right? Like first of all, like the data, robotic data is scarce. We don't have the luxury, although like I just said we have like the OXE data set. It's still, like not comparable by any means to the data sets that VLMs and so forth are being trained today. So, because typically a human has to like teleoperate and supervise the robot. So, collecting robotic data is really, really expensive and very time-consuming. So, that's one of the issues. Additionally, robot data is highly multimodal and heterogeneous, as instead of just like training only on natural language, we have several sensing modalities we need to interact with in the real world. And every robot has typically different sensors and actuators. So that makes it also like more challenging to scale and to learn from. Besides, for robotics, we typically need to run this in real time. Like so the model size actually matters. We can't take, I don't know, like ChatGPT, like 100 billion parameter model and put it on our quadruped because we can't like, we can't wait for a minute for, the ChatGPT API to return an answer on what the next action should be. We really need like fast real-time control. And finally, evaluating also our models with real robotics hardware is actually quite tedious and inexpensive too. So to to begin with, we will start in the course looking at the algorithmic frameworks commonly used in robot learning today. These can be broadly classified into two major families that we will cover extensively throughout the semester. On the left, we have imitation learning, which you can think of as supervised learning for the physical world. So this means that given a labeled action data set, our goal is to learn a function, as is showed in the example before, that maps an observation to an expert action. And this traditionally, this framework assumes that the inputs are IID, meaning they are independently and identically distributed. This means that each point does not influence any other data point, and that all points come from the same data distribution, underlying probability distribution. And so a lot of classic machine learning theory makes this assumption, so that, for example, if your training data is IID, then your training and test performance are mathematically linked, for example. And then on the right, we have reinforcement learning, where the objective changes from a behavioral cloning to learning a policy that, given a state, is able to predict the next best action. And this is typically done through trial and error within an environment to maximize our reward. And crucially, in robotics, here the data is not IID. So this means that your actions, when you take an action with your robot, this directly affects future states, creating a complex feedback loop, where, as I said, your action dictates what the robot will perceive next and also learn next. So now, bear with me. We're going to start slowly this semester. In the first half, we will focus on learning the fundamentals and the algorithms. We will start next week covering the basics of robot control and Markov decision processes, which will provide the mathematical language we use to describe robot environment interactions. From there, we will dive deep into the two algorithmic families I just described, imitation learning and both online and offline reinforcement learning for robot control. And to ensure that you kind of understand the algorithmic frameworks, we will start to ask you to implement these concepts in simulation for your first assignments. Not the first one, but I think after the second or third. Here we also have created, I think actually Liam created this simulator in Mujoko, which is using the same SO101 ARM that we will later use for the real group projects, like this fleet of 50 robots that we mentioned before, so that we have some consistency, and maybe then you can reuse some of the code you wrote for your individual homework assignments for your group project with the real robot, because it will be the same environment. In the second half of the course, we will shift gears from the fundamentals to, kind of the most exciting research that's happening in the field today. I call it scaling robot learning, for lack of a better name. This is where we will move beyond, the algorithms for the single task models and explore a bit how to build more general purpose robot brains that we discussed earlier. And we will kind of give an overview and dive deep into architectures, core architectures of the foundation model era, including generative models, learning how robots can imagine future states to plan more effectively, sequence modeling, and transformers, where we will apply or learn the same architectures and attention mechanisms that power GPT, but to the world of physical actions, or world models, high-level reasoning, and so forth. And as I said before, the video is not playing. As I said before, this is essentially the robot we will use for the group projects. So this is the SO101. You can see here someone is doing the puppeteering to collect some data with which then we can train some things. Okay, I'll try to cut it short. So the goal of the course really is to inspire you that robot learning is a cool field. We hope that after the course you will understand how we've gone from the 2007 Stanford PR1 demo, which was doing tidy up tasks but with teleoperation, to the latest, like really impressive videos you see from companies like Physical Intelligence, where if you see, like, it's essentially like the same tasks, but now it's like autonomous, right? So I think that's like super cool to understand how we've gone from like the teleop demo from 2007 to something that seems to start working and doing like this task. I think that's super exciting. Similarly, we can also look at the field of autonomous driving to kind of see the same paradigm shift, where we've moved from the DARPA self-driving challenge in 2005, where vehicles like struggled to navigate deserts using like all these sensors and kind of like the probabilistic robotics kind of like modeling framework, to the latest demos where the Tesla, the new Teslas drive themselves to the new owners, which I think is pretty impressive that they can do like automated delivery. Probably like only if you live close by to the factory or something, but like still like it's pretty cool. And so we will focus more on manipulation in this course, but the same concepts and algorithmic frameworks that have driven progress also work in self-driving cars for sure. And finally, also for humanoids, right, where you can see that we have moved from the DARPA Robotics Challenge, which I was showing before in 2015, where even the most advanced humanoids were struggling with these basic capabilities of like even opening a door or like walking straight, to the really like startling dexterity of like the latest like figure demo that is like super smooth and dexterous, and really like and this is like also result from all this like robot foundation modeling, and whether it's self-driving cars in a city or a humanoid preparing a meal, the underlying shift is kind of the same, where we are moving from like hard coding and towards the era of like learned physical intelligence. And so I hope that by the end of the course you will understand like all the algorithmic machinery that makes this transition possible. So I want to finish today's lecture with this question: why should you study robot learning? As I said before, the field offers the field is incredibly interdisciplinary. It requires really a broad and unique skill set. Like you aren't just like a mechanical engineer or a software engineer. Like you are working really across the entire stack. And in this course, like you will touch everything from high-level reasoning and foundation models and training to low-level like PID controllers for the robots, right? That make the actual robot move. Second, like the advances are universal. As we see in the algorithmic frameworks that you learn here are applicable to almost all robotic applications, from self-driving cars to humanoids or robots exploring the space. And I think that, as I said earlier, these are one of the most exciting times to be working in robot learning, and maybe the advances that you will make one day will bring us to the ChatGPT moments for robotics. And with this, thank you for attention, and I hope you enjoy the course.